All right, everyone, welcome. It's my pleasure to welcome back Mike Freedman, who will deliver the third of his lecture series, The Universe from a Single Particle. So,
thank you so much. All of a sudden it's working. I think the problem is I'm hooked up to many mics now instead of one. I'll disconnect this one.
It's good. Sounds good.
It's okay?
Yeah, sounds good.
All right, we'll just keep it the way it is. All right, I don't know what happened there. So it's feeling a little nervous, but I think this will work. I decided to celebrate the tropical weather here with my conference shirt. So I should give credit for this, the idea behind this talk, to a conversation I had about 4 years ago with the Stanford physicist Lenny Susskind. I was trying to understand some of the things that black hole physicists worry about, and I was, learning about the degrees of freedom as they're understood around a black hole, the surface of a black hole, and there are these famous formulas of Bekenstein and Hawking about the area of black holes being proportional to entropy, and related to these formulas is the idea that there's a degree of freedom for every tiny little unit of square area around a black hole, 4 times a Planck square. And I asked Lenny whether I should think of it as like a little tiling by small tiles on the surface of the black hole, and each of those is like a spin. And he said, no, that's exactly the wrong way to think about it, because we know these things from the field theory, we know they have to interact all-to-all, like in the SYK model, these all-to-all interactions. So it's definitely not like a lattice of qubits. So I said, well, what is it? Where did these degrees of freedom come from? And he just said, no one knows. And then I thought, well, that's really a fascinating problem. If no one knows where the degrees of freedom in black hole or early universe physics come from, that's something worth thinking about. And that's what this talk is about, is where does the universe come from? So I'd like to make the general assertion that in this modern age, as things progress, that we're not asking more complicated and more sophisticated questions. We're able to ask simpler and simpler and more childlike questions as our knowledge expands. And I think we're at the point almost of being able to ask, why is there something? Why is there a universe? But I don't know how to address that at all. But I think we can ask the question, which is tantalizingly close to that: why is there more than one thing? So what I the theme of this talk will be that as soon as there is one thing, there's a possibility for it to bifurcate and become the multitude of things and particles that we know about in the world. So hence the sort of playful title, Universe from a Single Particle. So the overall context for this talk will be quantum mechanics and Hilbert space, and I'm not going to do anything fancy. So for the entire talk, Hilbert space will be finite dimensional, but the finite numbers that you would think of if you were trying to model this into the actual universe would be these very big numbers like Googleplex or something like that. That would be the dimension. And the thing we find empirically with the study that I'll explain is that under physically reasonable assumptions, Hilbert space is sort of unstable and wants to acquire additional structure. If it's high dimensional, it wants to decompose as to tensor products of factors. This can be thought of as a kind of symmetry breaking. A symmetry breaking between, you might say, Hilbert space, which is describing one particle with an enormous number of degrees of freedom, breaking down to describing a system of particles, many particles, each of which have a modest number of degrees of freedom. And it will be this sense in which one thing appears to be many. So if you're so inclined, you can imagine that there's sort of a Buddhist theme to this talk, that we're all this vibrations of this one particle, or however you want to think about that. So here are the actors in the story, all written out on one line mathematically. So Cn is the Hilbert space, finite dimensional Hilbert space, its inner product. Sun is its group of symmetries of the inner product. Little sun is the skew Hermitian matrices, that's its Lie algebra, so those are infinitesimal symmetries. And very interesting to me, and something that I learned to think about, partly from this Susskind school of black hole physics, is we should think about different metrics, meaning inner products on the Lie algebra. This is mathematically the same as different left invariant metrics on the Lie group, because once you have the metric on the Lie algebra, you can push it around by left multiplication. And then maybe the last main character is, once you have a metric on the Lie group, I'd like to turn that into a probability distribution on the Hermitian or the skew Hermitian matrices, just by taking some kind of Gaussian probability distribution based on the inner product with respect to the metric. So once you've chosen a metric on the Lie algebra, you can think of a Gaussian on that Lie algebra, but the shape of the Gaussian depends on the inner product you've chosen. And I've just written out what that inner product is in index notation. The upper indices there would be basis for the Hermitian or skew Hermitian matrices. And this is maybe the way a mathematician would write it. It's the inner product relative to that inner product. And then in red, I noted that you can't really turn the inner product into a Gaussian until you pick a temperature, inverse temperature beta. And I'll be pretty careless, as I've already been in this talk, of whether I include the I or not in front of a Hermitian matrix. So in the Lie algebra, it's the skew Hermitian, but in many contexts, it'll be easier to talk about Hermitian matrices. So powers of I tended not to worry about. So this symmetry breaking idea that I already mentioned can be thought of as kind of a crystallization of the metric, given a potential, which is a functional, I'll call it delta, on the metrics. So imagine we have some functional on the metrics on the Lie algebra, or metric left invariant metrics. Say we have some functional, and I'll talk about choices of that functional very soon. Then once we have the functional, which I'm kind of picturing as some graph like this, the x-axis is this huge dimensional space of metrics on SUN. SUN is, the dimension of SUN is quadratic in n, and the metrics are quadratic on that. So the dimension of this space is proportional to the fourth power of n. So it's a very big x-axis there. And imagine some kind of landscape which is given by a functional. And what I'm saying here is that once we pick the functional, which we can look at a local minimum for the functional to pick out a metric, and then once we have that metric, we can imagine drawing randomly at a certain temperature from the associated Gaussian to get a Hamiltonian. And that, might be like the initial Hamiltonian of the universe. That's what it's H universe. And I'm just choosing a formalism for the drawing from the Gaussian with respect to a Boltzmann distribution, some Boltzmann-like distribution. And this is a little fishy, and I admit it right from the start, because usually Boltzmann distributions have to do with equilibration into an environment at a particular temperature. And since I'm talking about the entire universe, there's nothing else to equilibrate into. So my only excuse for using this is it's a reliably good idea in physics to recycle formalism. If Lagrangians and Hamiltonians are invented for one purpose in the 18th century, that doesn't mean they're not the right thing in the 21st century. So you'll see a lot of formalism recycled in that way. So I wanted to start out with a very concrete example of a functional, and this was the one that I first considered. Oh, and as I say, I first considered, let me just back up a few slides to mention my collaborators. This work was, all of this work was done with my postdoc at Microsoft when I was doing the work. Moji Sokrianzini, who later moved to the Perimeter Institute and then started a quantum company, Xanadu. And the last part of the work, which has to do with initial state as well as initial Hamiltonian, Adam Brown from Stanford and Blue Shift joined the project. So remember, delta is supposed to be a functional on metrics. So this is a little much to wrap your head around. It's, you know, we have an inner product on the Lie algebra, this huge Lie algebra, and we want a number, you know, what's the loss or whatever, you know, loss function, what is this? So as a geometer, the very first thing I thought of for a loss function would be Ricci scalar curvature. That's something you can compute, because if you have an inner product on the Lie algebra, as I mentioned, it gives you a left invariant metric, and since it's a homogeneous space, the curvature is the same at every point. So if you wanted some number, the obvious number to write down would be the scalar curvature, which the physicists call the Ricci scalar. So one nice thing about the Ricci scalar curvature is that if you look up old papers from the 70s by John Milner, where he discusses how to make computations of curvature on left invariant metrics on Lie groups, you can extract from that paper, not in this very slick diagrammatic formalism, but you can extract formulas for the Ricci scalar in terms of the two tensors that are in the game. So the trivalent vertices in this picture represent the structure constants of the Lie algebra. So those are three tensors, because what a structure constant is you pick two directions in the Lie algebra, you take their bracket, and you expand that back into the Lie algebra. So that's the kth component of the IJ bracket. So that's part of the data for the Lie algebra. In fact, that's all the data for the Lie algebra. The other data is what we supply, which is the metric. And G's with lower indices are, oh, I'm sorry, there's a typo on this slide. G's with lower indices are metrics, and G's with upper indices are inverse metrics. And in the pictorial calculus, the lower indices are G inverse, and the cups. The cups are G's and the caps are G inverses. So what I tried to do, I correctly wrote the diagrammatic formula, but there's a mistake. Some of these indices should be
K prime should be something.
yeah, some of the upper indices, you can figure it out. Yeah, the K should be down, so they cancel with the K's that are up. So thank you. So if you haven't seen this notation, like look in the Wikipedia article on Penrose tensor notation or something. But the basic idea is that you write a tensor as a vertex with some legs coming out, and the legs are copies of the vector spaces that are kind of coupled together by the tensor, and that if you have an upward and a downward thing connected, like here's a downward thing connected to an upward thing, you don't need any copy of the metric because you have a covariant index and contravariant index, and they just eat each other. If you have to turn the thing around, you need a copy of the metric, or if you turn around the other way, you need a copy of the metric inverse. So some formula like this, if you put the K's down, is the same as a diagram like that. So anyway, we thought what could be more natural, and Einstein would approve. So why not study the Ricci scalar? Well, in practice, we found the Ricci scalar was very hard to work with. It turned out that the landscape is quite flat, and when you look for minima numerically, you get stuck all the time, and the gradients are small, and it's hard to find them. And in fact, we were worried for a while that we weren't doing the numerics correctly. But then in the literature, we were able to find analytic computations of the critical points. And we were able to verify that there were local minima by setting our guess at the answer and then perturbing around it. But it was sort of a lesson that Ricci scalar curvature, for all its simplicity and beauty, was maybe not the best functional to work with. So we picked a different suite of functionals, which turned out not to be too important, and I'll say why I know that. But if you look at the form of this functional, it'll be familiar to you if you've ever taught a course where you did like perturbative 5-4 theory or something. If you did quantum field theory and it expanded as a perturbative series, what happens is you write down some exponential, which has a big quadratic piece, and a small correction at higher order perturbation, and you expand this integral into an infinite sum of diagrams. And like what they do at CERN for their problems is they truncate these, and then they sum up as many diagrams as they can, and then they get some approximation of the field theory prediction. So our challenge, this is not exactly that, and the difference is that these are tensors instead of scalars, but this is the, you might say, these are called Feynman integrals. You might say these are the Penrose analog of Feynman integrals. So we just thought this was the most natural functional, this was the most natural class of functionals that you could make if you're handed a quadratic and a cubic tensor. And it gets a little complicated, I won't go into the details. The reason like there are 3 copies of G down the diagonal is, regardless of whether you decide to consider this as a bosonic or fermionic integral, you have some problem about preventing one of these 2 terms from just canceling out by symmetry. So in order to prevent the cubic term from just zeroing out by symmetry, you have to play around a little bit. And all I want to say about this formula is it's this simplest thing that I think anyone can find. It's certainly the simplest expression we could find that give you non-trivial perturbations to the obvious quadratic integral. So these were the kind, and then the other nice feature of working in a perturbative regime is it gives free parameters. This expansion parameter k is up to us, and it turned out to be very useful to have these expansion parameters for the numerics. That empirically we worked with k roughly about 0.01, 1/100th, and in order to avoid very glassy landscapes with many, many local minima or very small gradients, we had to choose the perturbative expansion carefully. Okay, so we found local minima numerically, loads and loads of them, and I'll show you some of them very soon. And about 25 to 30% of these local minima that we found, in the dimensions we studied, which were first, we picked n to be, that capital N, we picked that to be either 4 or 8. We tried higher numbers, but the numerics was pretty difficult. Because remember, like I think if n is 8, the space of metrics is almost 2,000 dimensional. But the surprising thing is that a very large percentage of these local minima had a remarkable structure that I want to explain to you. And we coined the word CAT for knows about qubits. So far there was no input of tensor factors. That's the theme of this talk, that a tensor product emerges at a local minima where you didn't put it in, but it's an emergent thing. So let's say first, mathematically, what do we mean by a qubit structure on a Hilbert space? Well, the first thing is the Hilbert space better be a power of 2 dimension, or it can't possibly have a qubit structure. If it is a power of 2 dimensional, then the qubit structure is this isomorphism capital J from C2 to the n to the space. So there are different structures, and technically you regard 2 structures the same if you changed by SU2 or inside those factors. It's really the quotient. And such structures induce isomorphisms on the Hermitian matrices, or you can add an I and make it skew if you want, in this way. That is, such a J induces a lowercase j between the n-fold tensor power of the 2x2 Hermitian matrices, which come from the infinitesimals here, to the large Hermitian matrices. So we say that this metric on the Lie algebra knows about qubits if there exists a tensor structure, and I'll write the lowercase j, such that the metric has a basis of principal axes of this very particular form. So what are principal axes? They're basically the same as eigenvalues, except that would require lowering or raising an index to turn it into an operator, but it's the same thing. You have we used as the reference inner product the L2 inner product, or the killing norm, killing form. And then once you have a reference inner product, any other Gij should be thought of as like some high-dimensional ellipsoid in the Lie algebra, and it has longest directions, that's like the major principal axis, and then it has a second principal axis, and then a third and a fourth, and then a 63rd. There'd be 63 principal axes if n equals 8, because it's n squared minus 1. So we have all these principal axes, and we say it knows about qubits if these axes, which are Hermitian matrices, or I times a Hermitian matrix, if each of these axes is under this isomorphism J, 2 by 2, tensor product of 2 by 2. So it's a remarkably rare condition for 63 vectors, say, in this Lie algebra to tensor decompose with respect to the same tensor structure. If you ask what's the chance of that happening at random, it's like, 1 in well, of course, it doesn't happen exactly, but it happens, when we say it knows about qubits, it happens to high numerical precision. And one of the saving graces is we never had to think too hard about where the numerical cutoff was, because it turned out that when things were close, they were very, very close. So we found anything that was like less than 1% off, we allowed in the L2 norm. But if we changed that to 10% or 0.1%, it changed almost nothing. And that was quite reassuring that we were finding a real thing. So maybe this is a good moment to give examples of metrics that one might find or one might look for. So I already mentioned kind of the starting base point metric, just the killing form. And this metric, if you look at the probability distribution associated to it, is just the unitary Gaussian ensemble, GUE. That's the usual way when a physicist says select something at random in the Lie group or in the Lie algebra, that's what they mean. But in the last 15 years, from two sources, which used to be very far apart, quantum computation and black hole physics, independently suggested a different metric. And I associate on the quantum computing side Michael Nielsen, and on the black hole side Lenny Susskind and Adam Brown. So again, let's let n be 2 to the n, will be in a power of 2. Then these Brown-Susskind metrics are diagonal in sort of the polyword basis. So remember I noted that the Hermitians in the big space are tensor products of the Hermitian in the two-dimensional spaces. The Hermitians in the two-dimensional spaces have famous names that the physicists have given them: 1, x, y, and z. Those are the like 3 2x2 poly matrices. And so there's a weight of for a poly word, which is just the number of times something other than 1 occurs. And that's a very important thing physically, because what that means is, if you think of this as a term in a Hamiltonian, this is telling you how many bodies interact with each other. When you have identity, that means nothing is happening there. That degree of freedom is ignored in this interaction. If you have just one term, it's like a single site acting site-wise, like a magnetic field is rotating a spin. If you have two terms, that's kind of the most interesting thing. That's like a ferromagnet or an antiferromagnet. They're trying to align or disalign with each other. And then 3 terms is rare in physics, but that's still important. And so it's kind of natural to think of a metric that decays, whose strength decays with exponentially perhaps with the number of bodies in the interaction. From the quantum computing point of view, this merely expresses the financial difficulty of arranging, building a computer that can accurately couple many different qubits. If you wanted your gate to take 6 qubits and do something repeatable with it, that's probably 10 to the 6 times harder than getting 2 things to interact. So you imagine if you're doing a quantum computation that you probably want to break it up as maybe 2 by 2 or at the most 3 by 3 gates, and not try to have your gates 10 by 10 gates. So that was the idea. Nielsen's idea was that instead of costing quantum algorithms combinatorially by how many gates do you have to do to approximate something, he wanted to look at this exponentially penalized metric, get a C infinity metric on the Lie group, and then ask what the geodesic distance was from the identity to the group element that implemented the algorithm that was desired, like Shor factorization. So that's where it came from there, but in the black hole context, this idea that these all-to-all interactions are important, but they should become less and less significant in the physics as the body number increases. And some of the most famous models, like the Kitaev model, so-called SYK, which is a fermionic version of this, involves the interaction of four Majorana fermions, which Majorana fermions have quantum dimensions square root of 2, so that's really the fermionic version of a 2-body interaction. So Kitaev cut it off at 2 and said there's no interactions, but since then people have generalized the models to allow higher interactions with decay.
Quick question.
Yeah.
This is some weight on polynomials, but like, what do you do for a linear combination with them?
Oh, well, but the metric is diagonal in this basis.
Okay.
So you have a 2 to the n by 2 to the n matrix for the Gij, and it's just zeros except on the diagonal, and you have these exponentially growing numbers as you get bigger and bigger interactions.
Okay.
Any other questions? So here's data from the numerical studies, and I have to thank Microsoft for their tolerance. I don't know how much money we spent, but we spent a lot. So in the first functional scalar curvature that we considered, we found local minima, but as I said, we had to cheat to find these local minima. We looked in the analytic literature, and all the local minima actually involve decompositions of the Lie algebra into sub-Lie algebras. So this, I wrote SB2 here as a little reminder. SB2 is 10-dimensional and sits in this 5-dimensional SU4 Lie algebra. Sorry, SU4 is 15-dimensional, SB2 is 10-dimensional, and the 5 is the perpendicular directions. So here we found actually the spectrum to be, or the principal values to be highly degenerate. That is, we found 10 principal values that were the same that spanned the SB2 directions and then larger. And then there was also breaking to SO4 inside SU4, which is 6 and left over 9 dimensions. And we kept that pattern going. If we found a local minima, if there was degeneracy in the spectrum of the principal values, we list the strongest, the largest principal values degeneracy first, and then the second strongest principal values degeneracy, and so on. And what these, so CAC I already explained, these are ones where we could numerically verify that these lined up very well with qubit decompositions. And sub was, we were trying to keep ourselves honest. That stands for sub-Lie algebra. So we thought it was worth noting that some of the things we found corresponded to these sub-Lie algebras, so they might have nothing to do with qubits, and it's a coincidence that the structure can also be described in terms of qubit decomposition. But as we look through functionals where we can actually do the numerics better, and these are our nicknames for the functionals. I think I had, on the previous slide, I showed like Fs with various subscripts, but 2.6 just means we kept the diagrams that had somehow the parity for the non-zero diagrams in this functional had either 2 or 6 vertices. Those are the C's, and this had 2 or 4. So, by the way, I forgot to fill in a point. I said that you shouldn't worry too much about the form of the functionals, and the way I know that is early on we made several mistakes and had certain diagrams in the expansion that didn't belong there, or we had calculated their coefficients wrong. And when we found the local minima, nevertheless, we found CAC local minima. So that convinced us that there was nothing terribly magic about the functionals we had chosen. So I think that the real phenomenon has an additional layer of probability. I think that there's probably a large family of potential functionals that one could think about, maybe any functional that has a reasonably short description or something in terms of the relevant local information, the 2 tensors, probably produces similar stuff. And this is a great example of knowing additional stuff just by not being very smart, making a lot of mistakes. So, so I guess the thing to note, just before I leave all these different functionals, we find these different things. I guess each row of numbers corresponds to a local minimum we found. Each row should add up to 15 because here we're doing SU4 metrics. And we put this one little oval here. Notice that this looks like a row of Pascal's triangle, if you're willing to consider numerical error or something responsible for the, no, that one's in order. That's okay, that one's okay. So this turns out to not know about qubits, but it knows about a emergent Majorana structure, which is kind of a fermionic twin to qubits. So I'll say more about that. Other things can emerge besides qubits. Okay, then we did the same numerics at much more expense on SU8, and we had to abandon the scalar curvature functional. We couldn't find anything with it. We couldn't find any analytic results. But we did find, again, some Lie algebras. Some of the algebra decompositions emerged, 30-dimensional Lie algebra in both functionals. Found it the same, regardless of which functional we were looking at. But then we found 2 or 3 other local minima. Now, we worried next about what happens away from a power of 2, and since all the machinery was set up, we just thought we'd run it and see what kind of tensor decomposition would emerge if we gave it a prime dimension, just to sort of poke nature in the eye. And we found that nature had an answer, and what it did, well, when we gave it 6, which is of course not prime, what it did is it found local minima. 3 out of 30 local minima we were able to find with our various functionals and coupling constants. 3 out of 9 out of 30 decomposed as a qubit tensor Q trip. That's cool. When we gave it 5 and 7, what happened is it chose to ignore a direction and then factor. And sometimes, actually in one case, I think it ignored 3 directions and factored this way. So, and this kind of intrigued us, because if we take seriously this idea that the interacting universe that we live in emerged by factoring some kind of random gigantic number, and that all the microscopic degrees of freedom descend from that, well, this random gigantic number probably was not a power of 2, so what happened? And maybe what happened is it discarded like a logarithmic size or a polylog size piece, and then factored the rest into like as a smooth number into small primes. But we call this the leaky universe. because it's like some part of the universe did not get the message that it was supposed to coalesce into interacting physics, and it's out there in its native, raw, brutal state doing whatever it does. And then the fear that immediately struck me viscerally was that my personal wave function might overlap with this unregulated sector of the universe. And then where would I be? You know, I don't think that that would be good for my health. So I was worried of leaking out of the universe, so that's where the name came. But please don't worry too much. I think there are worse things to worry about right now in our day and age. So I mentioned Majorana physics. We also found a few examples where it wasn't CAC, but it was CAM. It knew about Majoranas. And this is a very analogous thing. It means each principal axis represents some homogeneous polynomial of a certain homogeneous degree in the Majorana generators. So the Majorana polynomials, in the homogeneous polynomials in the Majoranas are just another way, another basis for generating the full Lie algebra. And we found that, I guess that's written here, the span of the homogeneous polynomials in the Majoranas A1, or the first, I guess, MA stands for Majorana, and the 1 means the first, and 2n is the last. 2n Majoranas is enough to generate in n-dimensional space. Remember, little n was my notation for 2 to the big N. So we also found this phenomenon, which I think is just the fermionic version of knows about qubits. So this, numerically, this also came up. And in fact, we found these metrics that were studied by Brown and Susskind to some degree of numerical certainty, though the fit is not perfect. So I'll show you our most exciting solutions in the context of Brown-Susskind metrics. So by the way, we found we cheated a bit, because we initialized these metrics hoping to be somewhat close to a local minimum and fall into it. So we picked like here the 6 came out of order. We thought that, well, maybe there'd be a degeneracy, which was 4, 6, 4, 1 for how many independent directions in each homogeneous degree there would be. And then we had some guess, which was the blue curve, and we initialized the eigenvalues and then let the eigenvectors slide all around and try to find a local minimum. And what happened is, from some initialization guess, they slid up and formed some pattern, which has a kind of a roughly exponential behavior. With the red curve being the best exponential fit to the data we finally got out. So I'd say this finding is probably the least solid numerically of all the ones I'm presenting, but there is a hint in low dimensions of these metrics that have been studied for a variety of reasons, black hole and quantum information, actually arising as local minima for sort of generic functionals in the space of all metrics. So this is the point my second collaborator joined us, Adam Brown. And actually he said, I talked him into joining this project because he said a very interesting thing at a talk I gave on the first part of the project. He was sitting in the audience, and then I asked, are there any questions? And he said, well, it's more of a comment than a question. Don't you think it's kind of dumb to just look for the initial Hamiltonian of the universe? Because what's interesting about the universe is the slow release of entropy over 13.8 billion years. And that's not a property of the Hamiltonian. It's a joint property of the Hamiltonian and the initial state vector. They have to be aligned in a certain way to evolve for entropy to evolve in that way. So you shouldn't really be looking for an initial Hamiltonian and its properties, you should be looking for the pair. So I thought that was a great idea, and it turns out that the formalism we use, these perturbed Gaussians, can be easily modified to include an initial state. So remember, many screens back, we had an x-axis, which was the space of all metrics on the Lie algebra. We can expand that x-axis to be the Cartesian product of all metrics and all initial states if we write the initial state as a projector, because then it becomes an operator. So it's apples to apples. It's the same kind of thing as the metric. So that's the projector J. So it just is added as a source term in the usual sense in field theory. And then we could look for minima for this enhanced integral that had a new variable. It had the source as well as the metric as its variable. And the structure constants are fixed, of course. That's the property of the Lie algebra. And then we did numerics. And what we found is we looked for solutions. Well, first we checked that the solution was just cat in the original sense, that it did split up, say, this is the case of C4. We did check that all the principal directions split up as Hermitian, 2 by 2 Hermitian tensor, another 2 by 2 Hermitian. So once that was done, then we took those minima, and there were many, all those blue lines, count them, there were 100 or so as we varied the functionals. We took all those blue lines, and we asked, what is the entanglement entropy of the initial state that was also found at that minima? And we got this blue distribution, this histogram. So the histogram isn't very interesting, it's pretty flat, except it has this huge zero entropy spike. So zero entropy spike means that fraction, it's like, I don't know, 10% or 20% of the cases, there's no entanglement in the initial vector. It's like the initial vector is something in one tensor factor, something in the other tensor factor. It's not entangled. And then we wanted to know, how rare is that? So we took 100,000 random vectors in C2 tensor C2. We probably could have done this analytically, but we were lazy. And we got some sort of almost semicircle law. And this has a little bit of a bump at zero compared to that end, but nothing like that spike. So the rest of the distribution plausibly could be drawn from this distribution, randomly. But this zero entropy spike is something novel. So it's saying that when you find this joint minima, the state knows about, we call it, I think we call it SCAC for some reason. What was that all about? It sort of doubly knows about qubits. Not only does the metric know about qubits, but the initial state factored itself. And then we did the same experiment in CA. And I didn't mention this in the earlier slides, but many of our minima for 8 factored as 2 times 4 rather than 2 times 2 times 2. And some of them factored all the way when we were just looking at the metric alone, but when we were looking for both together, we never found a factoring that where both the metric and the state broke up as tensor product, as pure tensors, which a point I'll come back to. So, but when we found that the metric broke up as either 2 times 2 times 2 or 2 times 4, yeah, I think, in this distribution, I think we included all, whether it was 2 times 2 times 2 or 2 times 4. And then we asked the separate question whether the initial state also broke up. And you see the same thing as before. This is again 100,000 samples, and this shows this shows the entanglement entropy of a random vector within a twofold tensor decomposition of this kind. And there's certainly no zero energy spike. And then we ask what the entanglement vector is of our initial state experimentally, and actually it does look rather like it's drawn from this distribution, except for this big spike at zero entropy. Same, very often the state has low entanglement, so entropy would increase only very slowly under time evolution. Okay, so to sort of wrap up with the conclusions, I think the main conclusion we found is that nature abhors a naked Hilbert space and would like to dress it with some additional structure, a tensor structure or a Majorana structure. And in the Majorana case, groupings of principal values, principal axes, roughly obeying Brown-Sussman exponential penalty factors were observed. When we took random initial dimensions that are not powers of 2, we saw in the very low dimensions, and guess as if we went to higher dimensions, that a small fraction would be removed, resulting in a smooth number that factored into qubits, qubits, small local degrees of freedom. And this removal of a small section before factoring into many-body physics, that was what we called leaky scenario. Then with Adam, we added the initial state to the Hamiltonian by adding a source term, and we found that and studied the production of entropy over timescales. And now I want to claim that that we saw a glimmer of space-time in a way. We saw a glimmer of interaction of a lattice. So let me explain this last point. Even though it's in my conclusions, I haven't hit it yet. So let me back up to the previous slide. So let's consider the case when the common case when the Hamiltonian factored all the way 2 times 2 times 2, but the initial state only factored as 2 times 4. And if you try to, when that happens, there's a very interesting thing to look at, which is you look at the piece of the initial state that's in the C4, and you ask, what the hell's wrong with you? Why aren't you factoring the way you should with respect to the tensor decomposition that emerged on the Hamiltonian side? And we sorted around kind of desperately trying to look for examples where it factored. And to our surprise, not only didn't it have zero entropy, but the average entropy for that last decomposition was higher than average. It wasn't just that it wasn't showing, it wasn't just that it wasn't favorably inclined to break up as a pure tensor in those last 2 factors. It actually looked like it was fighting this, that it was like a Heisenberg interaction or something of the kind between the two. So it was really trying not to factor. And if you think about this, you might imagine, and I think I put this as my last comment, that we don't want to really, we wish we didn't have to stick with like 8 dimensions to do the numerics. We'd like to, people who do string theory think the good model for the universe, at least a bosonic stringy model, you should start with the Leach lattice, which is in 24 dimensions, and it's related to this bosonic string theory in 26 and all this. And in fact, it was a suggestion of Greg Moore when I talked to him that we should try to see Leach lattice structure emerge. So what did he mean by that suggestion? He meant that we should consider so many degrees of freedom that we have a chunk of a Leach lattice. Now that's a lot of degrees of freedom, because that means, Leach lattice has like 196,540 Kissing number. That's how many friends each one has. So to see that structure emerge, you'd have to have like that many qubits, so that each one of those dots that are touching each other is like a qubit, and you want the nearby ones to be interacting. So to do a numerical simulation on that, you'd have to have a Hilbert space that was like 2 to the million dimensional. So you need 1 million qubits on a quantum computer, and to do a big piece of the least lattice, maybe you need trillion qubits. But Greg's idea was, well, maybe what you'll see in this initial state is that or the initial Hamiltonian, is you'll be seeing that interaction is not all-to-all, but the local degrees of freedom start to sort of get exhausted. They can only interact with a certain number of friends, and that's what describes eventually the microscopic structure of space. That would be the idea, that a limited amount of interaction could eventually be where space-time or space comes from. So because of the paucity of our model, we couldn't do a chunk of the Leech lattice, but we can do 3 points. And what we find is 3 points, and there's a bond between one pair of them. We find that there's sort of some interaction going on between these two and not interaction going on between this one and those two. So a very optimistic view as we're starting to see the lattice structure, but that's really more of a joke than real. It's just a plug that we need to build a quantum computer with 1 trillion degrees of freedom, and then we can carry out the numerics. Or we need an analytical approach. Someone has to figure out how to understand this phenomenon, which so far I've just presented to you entirely empirically. But if there's using C-star algebras or something, maybe there's a way to think about this analytically and not have to rely on numerics. Because I'd really like to understand what's going on, not just observe glimpses of it numerically. Thank you.
Any questions from Mike? I have a question. So at some point you made this comment that like the choice of your functional didn't really matter that much. But there must have been at least some basic considerations of the parameters.
Well,
like,
yeah,
this
so
one will definitely not work.
Yeah. So there's sort of some. That's a very good question. Thanks for asking it. There's some entropic issue in the background here, because you have to think about how many functionals there are and how that compares to how restrictive the criteria is you're applying to local minima. Because it can't literally be true that the choice of the functional makes no difference, because there are a lot of functions. I could pick any metrics that I wanted, and then I could produce a functional where those metrics are the local minima. And then, of course, I wouldn't be seeing special properties at the local minima. But I tried to squeeze in a few words when I said that. I said maybe any functional that has a short description in terms of the C's and the G's. Because that's what we empirically have evidence for. I mean, there are a lot of functionals that you could state that you'd have no way to put on a computer. You could say, let's the value of the functional for a given metric be the diameter of the Lie group with that metric. That's geometrically a very interesting quantity, but no one knows how to learn anything useful about the geodesic geometry on these giant groups with arbitrary metrics. So all I really meant was that for calculational and maybe philosophical reasons, we wanted to restrict ourselves to functionals that could be expressed rather succinctly in terms of diagrams. And at first we thought maybe the diagrams have to be organized in some slick way so they relate to, some very simple perturbed Gaussians. But then we made some mistakes and we produced, I think by our mistakes, random functionals within that class of things that are linear combinations of diagrams. And they didn't seem to be, we didn't investigate this systematically because we only have limited computer time. But our glimpse into the world of these choices through mistakes was that it didn't make much difference. So that's all I really know, is that if you cobble together, here's a statement we do know. Many of these possibly all, this is a conjecture, but Some of the diagrams we can prove analytically are convex functionals, and they only have one critical point, and that critical point, either up or down, will be at the killing metric. So, but though they're convex, they're kind of wiggly. Some are up and some are down. And as soon as you take linear combinations of them, the fact that they wiggle in different directions then produces a pretty complicated landscape. So one diagram is probably not good, but is our experience of adding several diagrams together and taking combinations, that's the domain in which we found this cat behavior.
Any other questions? All right, let's, thanks, Peter.